detailed investigation that we did on switch power units that we tried to age artificially and check what happens to the EMC properties. So when did this all start? A couple of years ago, we were doing some tests with the Munster facility. Those guys are responsible for EMC and nuclear EMP protection for the German military. And we got back some long-range comm shelters. So basically just containers that were full of communication equipment. And when we tested those decommissioned shelters, we found some interesting things. So first, there was a negative shielding effectiveness. So basically, those are resonators, cavity resonators that were supposed to be RF-proof, but they were not. There were several additional apertures, and if you have a look on this photo here, you see those shelters include RF-proof doors. The trouble is, and we've all worked with this kind of stuff, those doors are pretty hard to close. So, well, if you deploy those shelters to an ordinary soldier, so what they do is, if a door is hard to close, they just bang it shut, and several of the RF-proof fingers here, so made from coppers, were broken. And now then we got this idea, well, if this happens to any kind of equipment that was, of course, tested before deployment, is there anything going on with any other component for RF communication, for EMC or whatever? And the problem that we are dealing with is that the EMC tests for any kind of equipment in the whole world, independent of Arabia, China, US, Europe, or wherever, they are tested with prototypes or pre-production samples, usually built from better material than the line assembly will give you. And once they are tested and once they are checked and they comply with the EMC regulations, they get a nice sticker which tells the world this equipment complies with the EMC regulation and thresholds. Trouble is that many devices are going to be used for a long time, and this would mean in the end that the EMC properties can, of course, change over the lifetime. When we started to discuss those things, we came up with some very interesting topics that we wanted to investigate. So you are going to see degradation of components of any electrical or electronic component. Capacitors come into mind on the first place. Semiconductors, that's not such a big problem. Isolators of spark-up elements. Extra trouble is if you apply very rigorous EMC tests like HEMP, so EMP tests. Those might, well, mechanically destroy protective devices, and this would mean, well, your device is going to see the it's going to pass the test, but maybe the protective elements are destroyed. So, possible solutions for this? Well, you could repeat the emissions and as a susceptibility test during the lifetime. You could apply a more strenuous test during the certification problem, which in EMC terms usually means that you apply a higher magnitude. But this is not working here, by the way. I'm going to show you later. Or you could apply artificial aging during the certification process. And this is a line that we are going to talk a bit about later. So what effects could occur? So, and my nightmare is we are all going for smart grids. So we would like to adapt the consumption of electrical energy to the generation. Smart grid means you have a power switch down in your basement, switching or connecting to the power grid every time that the energy is available. And again, if you have, as an educated guess, a lifetime of a smart grid installation of about 10 years, with possible degradation in the last years, you could run an estimation. And we have 40 million households in Germany. And what if you have 10%, so 4 million power switches down in the basement that show degradation. What is the effect on the power grid? So this is something that we decided to have a look on. In cooperation with the University of Coimbra in Portugal, we started to investigate the aging properties of components by artificial aging, and we wanted to estimate the degradation effects. We're still working on this. So just to keep you to keep this in your minds, what is the aim of an EMC testing? So we should guarantee the functioning of electronic device in a normal signal environment. So this means, well, you should grab a normal component, you make a test, and if there's nothing untoward happen, like, well, EMP or use in a highly industrial area, the device should be working. Second, we should guarantee that single devices do not emit too much interference, and military tests are prescribed by regulations. Again, only for once in a lifetime, and with a prototype series. Well, this is for all electronic or electric devices. The good old days were the days when this was aging was not important, because okay, this is a British-style World War II utility receiver, and back on those days, you bought a radio for life. So you invested lots of money. You bought something that was not supposed to break down within the next 20 years, and this was built from high-quality components, meaning that in the end you would get an appliance that would not fail the EMC thresholds during the whole lifetime. The trouble is, well, you needed to run tests in all relevant modes of operation. Rather easy for this device, rather difficult if we move on to rather more complicated devices. So with an analog radio receiver, you have two states: you have off, you have on. You have a couple of parameters which are rather low, so you can choose the frequency of the receiver, you can check the volume, and that's it. Trouble is, this is not the kind of equipment we are talking about now. Okay, and coming back to aging, there are not many components that can influence either one of those states. In a computer, in a modern computer, there are a lot more things. So you have a lot more states. So off, okay, no aging here. Booting, this could be radically changed. A computer could be on and inactive, just waiting for orders after booting. It could be on and active. It could be idle. It could be going to power save, and there is the interaction between those complex states. And even during those states, you have several parameters that define the EMC parameters. So the computer could be accessing the hard disk, so shoveling a lot of data to the disk. Could be accessing the peripherals. It could be accessing the network. Could be going into number crunching mode, very common at our lab. It could be a multi-processor computing with a high amount of network data transfer. It could be connecting to the USB and external device. It could be communicating with the power unit, so in here between idle and the power saver. And every kind of state must be tested, and every kind of those states could be influenced by aging. So now let's have a detailed look on what could be going on and what could be a cause and effect of aging components. So the possible effects are listed here. First of all, we came up with the idea that there is going to be thermo-elastic stress on the components. So this is usually coming from different outside conditions. Well, now your device is sitting in an office and it gets colder at night, warmer by daytime. Gets even worse if you're not inside a building, but let's say in a tent, shelter, or whatever. If this is going on, you could see some breaking of the solder joints, which would render the equipment useless. you could see the degradation of capacitor because the dielectrics are going to be macerated, and you're going to see the degradation of semiconductors. This is like the semiconductor material diffusing out of the semiconductors. Effect would be a failure or degradation of protective element. Repeated switching, you're going to see degradation of capacitors for the same reasons as above. So we are going to see degradations of filters. Two more things that we wanted to investigate but didn't for lack of funding at the moment is chemical stress. So there could be a corrosion of metallic parts, meaning degradation of connectors. This could be especially bad if we talk about those long-range communication shelters. So if they are deployed somewhere near the sea, you're going to see sea spray, which is going to corrode those RF-proof doors a lot, and you're going to see maceration of isolators, and which are going to be the degradation of cable shielding. And by the way, this is going to be interesting for guys like Shaoki, when they try to attack any device with IEMI. Radiative stress will be important for space or nuclear reactors only, but we didn't go into detail here. Although I think we found a nice way to conduct tests like this in the future. So thermo-elastic stress is going to be affected by repeated heating and cooling, leading to repeated elongating and shrinking of metal components. And this could mean that the joints are going to break. Bleeding of material from capacitors or semiconductors will downgrade the components. So nothing new about this. This is something that we are going to see later in the test with the power supply units. Repeated switching is something that we took into account very early. So because any kind of electrical or electronic device is going to be switched on and off repeatedly. You're going to see probably thermoelectric stress on top, which is going to be worsened if you don't switch at the zeros of voltage and current, because you're going to see much stronger transients. As a first step, we had a look on several devices and try to estimate the number of switchings for normal operations. Chemical stress, again, this is going to lead to maceration of isolators. Those isolators that are exposed to corrosive agents, saltwater spray, rain, or whatever, or ionizing radiation, will degrade if they are exposed. Corrosion of connectors will degrade the conductivity, and this will increase the resistivity of the line and limit the effectivity of the device. Mechanical stress, okay, this is where we started from. Repeated open closing of aperture, repeated bending of cables and connectors. This is going to be addressed in the later phase of the project. The effects that can be imagined is, okay, the trouble is that those degradations of failures can appear with devices under test with a mandatory very low probability of failure during operation. So, like it's listed here, it's aircraft, spacecraft, satellite, security devices, so police radio, military radio, or whatever. This is relatively uncritical for automotive appliances because the usual reactor of a modern car, which is governed by a central computer, is, if anything untoward occurs, the car will stop the motor. We had some nice tests with IEMI for car stoppers. The trouble is that you should critically check if some of the critical components of the car can be affected. So this is, well, imagine if an unwanted signal tells the brake to go into full brake mode while you're driving around down the motorway. It is really critical for spacecraft. Well, for obvious reasons, you can't send someone up to repair the spacecraft during a mission. And critical failure could even mean the loss of the spacecraft if an engine failure occurs. All the stuff is really uncritical for aircraft because the usual maintenance plans include a disassembling of the aircraft at regular intervals, plus automatic maintenance that regularly automatically checks any component and tells you if there's some issue. And some issue usually means there's a technician coming out, which is going to replace the critical unit. So degradation of filter components will be critical for a large number of devices, as I told you before, power switches as part of power distribution grids. It's again critical if low failure probability is needed. So we talk about, let's say, EMP filters for hardened system. You don't want them to fail in case of an event. Lightning protection filters for aircraft, rather critical because unlike one aircraft company told a friend of mine, our aircraft are not hit by lightning. This is happening regularly. And of course, automated systems are going to be affected in traffic and logistics. Degradation of cable shielding. This would mean external interference are going to couple more effectively into hardened system, and they can have effects on emission security. So, but now to the main part. We ran some selected tests for power supply units for computers, and I'd like to share those results with you. So why did we pick this? Well, obvious reasons. Those thingies are known to be major sources of conducted emissions. Even minor changes of components can lead to increased emission levels, or even to exceedance of regulation thresholds. The power supply units for computers are relatively inexpensive. At our hand, an electrically with this is the amount of operations. We used 8 power supply units that we grabbed from decommissioned computers, well, in the first step, because there were no other available. And this is a short video of the switching suitcase. What you're going to see here is the relay. So those are 4 relays and 4 relays here. Control indicators that tell us that the channels are active or inactive. Those are current sensors that tell you if there's current flowing in the circuits or not, just as an additional control mechanism. And the clicking sound is the relay switching. And what you see up here is are those 8 power supply units that we grabbed from the decommissioned computers. And this is the LabVIEW control panel of the software. So the test setup, and I'll be quick about this. We grabbed this from the international norm 55022. So you have the equipment under test. You have the peripheral equipment. There is a virtual ground plane below and at the side. And you have a line-independent stabilization network, which you are going to see here. This is the LISN. It's all relatively far away from the objective, and this is the DUT. And you note that the conductive ground was acceptable for this test. And this is a conductive wall made from wire mesh because we didn't have solid aluminum available. What you see here is the average of the conducted emissions of 8 power supply units. In green, you see weekly the DOTs before the test, and in red the DOT after the test. Okay, 20 dB microvolt is not a very high value that is added to the emissions, but if you have a look on the relative changes, you see that the artificial aging can add up to 5 dB at certain frequencies. So, second test was done with newly acquired cheap power supply units. We checked them with an infrared camera to find out if the on-off times that we selected were okay or not. And what you see here is a component. I think this is a heat sink of the controller of the PSU, slowly heating up to a maximum value after about 2.5 seconds. So we picked our on-off times accordingly. We of course kept a control group of 4 power supply units that were not aged, just to check if there's anything untoward going on. Sorry guys, and I come from biological testing, you always need a control test group. The red line is a threshold given by EN 55032 for household appliances. The trouble with really cheap equipment is that some of those, actually the whole second batch that we used didn't meet the threshold even when unaged. Probably manufactured in a rather bad environment or manufactured on the Mondays. Those are the funny things that can happen to you during those tests. More important is this diagram. In the light green, you see the conducted emissions by one selected power supply unit. After 1,000 iterations, this is not bad. But after, let's say, 144,000 iterations, the thresholds are going to be exceeded by a lot. So this appliance would not be working anymore. The student running those tests came up with an additional idea because he had another week or so left for his master's thesis, and used one of those already aged devices and put another 100,000 iterations on it, which you see here. So this is getting even worse. Trouble is we are still looking for a student to continue those tests. So to conclude my presentation, if you apply artificial aging to power supply units, you're going to see changes in the conducted emissions. This is depending on the load, which I didn't include here. If you want to run some kind of test, welcome to parameter space hell, because for a detailed investigation that takes into account any parameters, you are going to end up with a really, really high number of tests. After many cycles, you see that emissions will exceed the regulations. The parameters of the on-off keying influence the artificial aging. Future research. So we are in the process of measuring the input impedance. Use this to model the input circuits and age only the input circuits of those PSUs in a lot higher number. We would like to model the changes into a lumped element model and predict changes, and of course move on to aging by temperature and humidity in a thermal cabinet. So. And this concludes my presentation. Thank you for your attention. And I don't know, Felix, if we have time for questions, but I'm more than happy to answer them.
Thank you. Thank you very much, dear Lars. Yeah, we have time. We have time for questions. We have plenty of time for questions. You already have several questions in the Q&A section. Are you able to see them?
Yes, I can.
So, if you please.
So, Jean-Philippe Parmentier, hi, JP. Seems I read the question. Okay, it seems to me that the EMC problems should include possible obsolescence of components as well as aging. Replacement of components seems to be very close to the degradation of components. Both problems are related to performance variation of an EMC performance in time. Can you comment on how and if your approach could and should cover possible obsolescences of components as well? This is troublesome because again, obsolescence just means well that devices are constructed in a way to break after a short term. And the trouble is you won't get any information on this because every manufacturer will tell you, no, our components are not built to break in time. But this is again troublesome for various reasons, because I think this will go down to component level even. But I think we should discuss this later on or in an offline meeting. We are discussing this at the moment. So what are what devices are subject to more to aging more? Old or modern equipment? Modern equipment by a mile. Because again, let's say, okay, I'm 50. When I bought my first TV, it was working for 20 years. The last one we bought was breaking down after 8 years for a very, very simple reason. Again, 20 years ago or 30 years ago, those devices were built to last from very high grade components. And nowadays, every manufacturer goes for the cheapest components available. Meaning, probably constructing the devices from cheap material, which are going to break down. Okay, can an IP-rated enclosure help the degradation? Yes, it can. From Jean-Philippe Parentier again, obsolescence meant for me to replace one electronic component from one manufacturer by the same component from another manufacturer. And now we are getting into a more and more interesting discussions, because again, some of the ideas came from EMP testing. So EMP testing is testing for susceptibility against electromagnetic pulses. So whether nuclear or artificially produced. The trouble is that we found out that those very, very rigorous tests can break components or protective elements. The usual thing during the EMC test is, well, you replace it, but in fact, replacing the component will change your device. And well, how can we well, the question is on how to move on with the EMC test of this device, which is something different right now. I don't know. We are still working on this.
Okay. So there is one last. Can IP-rated enclosures help against aging degradation?
Sorry?
So there is one more question. Can IP? I mean.
Yes, of course.
Yeah.
Although IP is usually waterproofing and dust-proofing those devices. And of course, if you run an equipment in a air-conditioned environment, this will decrease the mechanical stress. By the way, we had a nice one, a visit from a guy from a measurement equipment company, and for their very, very precise oscilloscopes. They came up with a trick where they preheat the interior of the scope to up to 80 degrees centigrade, which is fairly easy to manage and to keep constant. And they are not concerned about thermic changes in their equipment. But then we talk about a high precision one here.
Okay.
Great.
So if there are any more questions from the audience, there is a comment by Jean-Philippe. I think you get them. Get it? So any more questions from the audience? We still have a couple of minutes. Okay. If not, thank you very much, dear Mark, for this excellent talk with a very challenging topic. Very interesting talk. So see you in Abu Dhabi next year.
Yeah, by all means.
The joint conference. Thank you very much.